In this video, we are going to talk about the motion planning problem. By motion planning, we mean the problem of finding a nominal command profile so that the robot achieves a certain desirable motion. A command profile is a function that gives the commands to execute at each instant. We talk about nominal or open-loop command profile because during the execution there will certainly be noises and other disturbances that we will have to compensate using feedback. Still, the command profile would create a desired motion if there were no disturbances. A desirable motion is one that 1. Arrives at the desired configuration, 2. Does not collide with the environment and the other agents, and 3. Optimizes the performance objectives. There could be many performance objectives. We might want the robot to minimize the time to execute the trajectory, to maximize passenger comfort, to minimize fuel consumption, and any combination of these. We will talk later about the nuances of behavior specification. For now, we are concerned with the purely geometric aspect of the problem. Planning is a very broad and deep topic, and both science and industry are progressing rapidly. In these classes, we will look at the basic formulation of motion planning and some representative methods for planning for a self-driving car. We will try to be very specific about the limitations and the scope of what we study. Topic by topic, we will give pointers to where you can start learning about the more complex extensions. We focus on the scenario of planning for autonomous vehicles, such as self-driving cars. Planning for a flying vehicle, like a drone, would have very much the same flavor. However, the methods we discuss would not be useful for robots like manipulators, which have very different characteristics. We will do planning in state space. This means that we assume that the controller that executes the plan will know the state of the robot. In general, this is not true, because the robot does not observe the state directly, rather the state must be inferred from the sensor data. We will not consider any form of uncertainty for now. We will only deal with static environments or environments with obstacles that have unknown motion. A large part of the complexity of AV design comes from trying to predict what the others will do and how they will react to the car's actions. We'll do motion planning. Vehicles accomplish their task by moving around, and without coming into contact with anything. But more generally, other robots need to change the environment. A manipulator might paint or solder a part. A robot nurse needs to open doors, and so on. Motion planning can be seen as an optimal control problem. Let's remind ourselves of what an optimal control problem is. To define an optimal control problem, we need to choose the state space X, the command space U, the initial state x0, and the dynamics F. Then we define the constraints that describe the feasible solutions. These are equalities, represented as a function h of x, and inequalities, represented as a function g of x. These define what are the feasible trajectories. We also need an objective that is a functional to minimize. Typically, to obtain an optimal control problem that is tractable, we have to assume that the objective is the integral of an instantaneous cost plus a final cost. Optimal control problems are solvable in a closed form only in special cases. For example, if the system and constraints are linear and the objective function is quadratic. Otherwise, we must rely on nonlinear solvers. We could cast a motion planning problem as an optimal control problem. The state space would include the robot configuration, that is, pose and velocities. The commands could be the actuator commands, which for an AV are steering, gas, and brakes, or idealized commands, such as velocity, assuming that downstream there is going to be a controller that will compute the raw commands given the idealized commands. The dynamics could be the full platform dynamics, or perhaps just the kinematics. The cost functional would model the preference for a short ride or a smooth ride. The final cost could be used to constrain the final configuration to be in a desired set. The constraints are used to model motion feasibility. The description of the environment would be encoded either in the function h or g. For non-trivial environments, these functions become highly nonlinear. This is one of the reasons one cannot use generic optimization-based solvers to solve motion planning over a long horizon. We cannot approach motion planning as a generic optimization problem. Rather, what is needed is exploiting as much as possible the structure of the problem, and in particular, the geometric structure of the problem. For this reason, most of the discussion will be about defining geometric concepts and their properties, and how we can operate on them. In this video, we have introduced the motion planning problem. We have seen that, although motion planning could be formalized as an optimal control problem, it would not be tractable. In the next video, we will go deeper into the geometric characterization of motion planning.